Right, before I hand you out the notes, okay, we're going to look at a couple of things first. Right, so we're going to look at what's called approximation method. So one thing that we will discover we can do with integration, it will allow us to find the exact area underneath a curve and the axis.
Is this used to do the things where they spin it around the y-axis and you have to find the area of it?
That's volume.
Oh.
Okay, yes, we'll get to that at this point in topic 2.
Do you have any more of those rules? Those ones that the car has.
What, the ones I've already given? Ones that I've already given you?
Yeah, mine died. I've kept it, but it died. And now I haven't followed it, so I won't break
If
it.
yours the only one that's like, no, just switch it, and then you want to do it again.
Because I appreciated the gift.
I appreciated it, but it broke the bottom of my hand.
Okay, so my question to you is, in what ways can we approximate the area underneath that curve? How could we estimate the area? Blocks of? Okay, so if we were to draw rectangles, okay, because of course they found out how to find out an area of a rectangle a long time ago. Okay, so we've made the rectangles the same width, okay, and we orientate them in that position there. Okay, that will give us an approximation to the area of between the curve and the x-axis. Okay, between A and B.
How close would that estimation be?
Okay,
How close would the estimation be?
it depends on the width of your rectangles. Okay, so how close would the approximation be? It would all be dependent on what width you make your rectangles. So if we make them smaller, the width smaller, we're going to have less of it peaking above the curve in this orientation. Alright, so that means the approximation to the area, exact area, will be better. Alright, if I only did 2 rectangles there, the approximation would not be very accurate compared to doing more rectangles in through there. Okay, now, not only that, so that's, we've done the rectangles above to give us an overestimate of the area. Okay, what we can also do is do the rectangles to touch below. Okay, and this will give us an underestimate. That will give us an underestimation of the area between the curve and the axis. Okay, so rectangles was the first thing that they came up with to approximate the area under a curve in calculus. Okay, so in your notes, when I'll get into it in a second, so the width of each rectangle is consistent and it's called delta x. You don't really need to know that except you two. That'll come up a lot for you guys. And the height of each rectangle is f of x. Okay, so of course if we have our curve, y is f of x. Okay, so the width will be delta x, and then the actual height of it will be f of x for each of the respective rectangles. Well, if you actually did a difference, your answer would be very close to 0, wouldn't it?
Not the difference, it's like the difference of just those 2 answers. So like all of that is counted as one measurement.
Mm-hmm.
So the under is like the baseline, and then the over is one.
What, from the actual curve to just above or just below? Yeah, we could do that. That could give us a better approximation. In most cases, yes. Good thinking outside the box there. Alright, so as delta x, so the width of these rectangles approach 0, Okay, so that in other words, the smaller and smaller we make these width, okay, the more accurate we will have our answer to be the exact area of there. Okay. So this is not really important. Okay, so as delta x approaches 0, so we're considering a limit for this. Okay, when we get to the value of 0 for delta x, we will have the exact area. Okay, so it's like when we did differentiation by first principles. Okay, as we approached as h approaches 0, we take that limit. Okay, and then we got the exact derivative from the function itself. So this is almost going backwards. Okay, so as we get delta x, the width of these rectangles as 0, okay, approaching 0, and we take it like a limit as we would take it to 0, we will then have the exact area between the curve and the x-axis between A and B. Okay, so area, which is not important, it's just to cover all bases, okay, is going to be the limit as delta x approaches 0, okay, of the sigma sum of the product to make each rectangle. Alright, so if you don't understand this, that's okay. It's not really important, okay, except for you two, that's why I'm introducing it. Alright, so each of these rectangles will have a width of delta x and a height of f of x, whatever the value for f of x is for what value of x you have down here. So, we're doing our sum, we're summing all those rectangles together, and we take the limit, okay, and that will result in the integration symbol. Alright, so it's like an f without the cross, nice, something like that, of our function of x with respect to x. Alright, and we'll talk about that more a bit later on. Okay, so that's just the introduction for what we're doing. Okay. We've just looked at rectangles. Is there any shape that will give us a better estimation and that we know how to calculate the area of? That we know what the area is, how to calculate the area of that specific triangles? So you're saying, are you saying that would give us some better approximation? No? What else? Squares? Yeah, it's good to put little squares up on top of each other there. Yep. What's another way we can not necessarily better than do that, but something more straightforward? Yep, which is called a... Yeah, so if we go back to this rectangle, okay, if we did this as a trapezium, okay, the property of the trapezium is that we have one pair of parallel sides. That's the only condition needed for a trapezium. Right? So we have the flat base there, that is the two parallel sides going that way, and we've got that slant height there. So in most cases, a trapezium will give us a better approximation than rectangles would. Okay, so if I continue that pattern for the same width, delta x, can you see that we're going to get a much more accurate answer above or below the curve? And I know, of course, everyone here remembers how to calculate the area of a trapezium. Hey? Yes, it was one of the questions in the 2014 HSC Extension 2 exam was, what's the area of trapezium?
H bracket A plus B.
Oh, close, not quite.
Oh, half H.
Now, of course, the question was a lot more involved than just finding area of trapezium, but to start the question, you needed to know the area of trapezium, which is Year 7, Year 8 work. Okay, so it's funny that some things you do in stage 4 maths is applicable in extension 2 HSC question.